All right. Hey, everyone. So welcome back. First up, we've got Aditi talking about worst case robustness in machine learning. So take it away.
Hi, everyone. Thanks to the organizers for inviting me, and thanks everyone for joining. So today I'll be talking about worst case robustness in machine learning. So this is going to be sort of a high level overview on the different kind of problems that we deal with when we think about robustness in machine learning, and how some kind of a bridge between worst case and kind of average case analysis could be useful to solve pretty much a still very open practical question. So to make sure everyone's on the same page, I mean, we've all seen really impressive results with machine learning in the past few years. For example, AlphaGo, GPT-3, AlphaFold, and if you're wondering what avocados in the form of armchairs would look like, ML can generate and tell us today. But not just these eye-catching impressive results, but ML is also widely used around us in many different applications like the ones shown on the screen. So what got me interested in robustness is to kind of look at how well does machine learning work in these real-world applications. Here is an example from 2015 that perhaps a lot of you are familiar with, where it was seen that facial recognition systems do not work very well on certain demographics, for example. This issue received a lot of attention, and it's been a few years since then, so you'd hope that things are better now. But in 2020, we see that facial recognition systems continue to make such mistakes, and this time a Black person was wrongly arrested. So I went back and saw what happened in 2015, how did they address this issue? And turns out that the fix they came up with was to remove the word gorilla from their captioning lexicon. So I guess it's no longer that surprising that some of these systems are still pretty broken. Here's another example of self-driving cars, which again, we've been hearing a lot about, but how good are self-driving cars? Unfortunately, we find that self-driving cars are actually not that great. And unfortunately, tragically, a woman was killed, where among other issues, the problem was that a machine learning model failed to recognize a pedestrian who was jaywalking because it was only trained to recognize pedestrians at crosswalks. I don't want to start this talk on a very dark note. So when I looked up for errors, I also found some funny things like how a soccer game was ruined because mistakes that a machine learning model can make. So what we find is that current machine learning systems are really brittle, and while they're very promising in terms of like all the impressive results that we have, they're also quite brittle in their current form. And as we use ML so widely in a lot of applications around us, and we're only probably going to use it more and more, a quite important question to think about is how do we make these systems robust? So let's look at the machine learning pipeline and think about where this issue is coming from. So usually what we do is collect a data set of examples. We split this into train and test, and then we train on the training data and we evaluate on this held out test set. So this is what a lot of us are probably familiar with. And most benchmarks empirically as well as theoretically study the setting. And a lot of open questions, and we don't completely understand this by any means. But if you look at performance in the real world, this is clearly insufficient, because what we really should be caring about is this wide range of examples that the model could encounter when it's deployed. For example, pedestrians who could be jaywalking. And so very broadly, like robust machine learning tries to deal with the question of how do we get good performance on a wide range of examples, even if a model is only trained on a particular set of particular distribution P. And especially we think about good performance outside this training distribution. So just to give a few concrete examples within the community when we think about robustness. So one example is security, where, for example, in content filtering, if you use a machine learning application, people are going to try to subvert the system and get their content through, and they're not going to restrict themselves to the training distribution. So it's important to think about performance outside the training distribution here. And even if there are no adversaries, for example, if you have self-driving cars or healthcare, it's really important to think about all the boundary conditions and the edge cases as well. Another important aspect is fairness across subpopulations, because in many applications, whatever distribution you've collected your training data from could encode biases, and it's important to go beyond that. Okay, so having kind of said the broad reasoning of why we should care about robust machine learning, I want to think more carefully about what's the objective and what changes when compared to standard machine learning. So we have this training data, we pick a model architecture, and then we optimize some training objective, and then we evaluate this model. So usually the training data is like some n data points from some distribution P, and we evaluate on this objective, which is just like how well some model does on new examples from the same distribution P. When I think about robustness, one kind of standard way to model this is like the robust optimization framework, where instead of just looking at performance on one particular distribution P, we define a ball around this distribution, and we look at how well a model does on new examples in the worst case around this ball of distributions around the training data. So instead of looking at performance on just one distribution, we look at how well the model does in the worst case over a ball of perturbations around this particular distribution. So usually what happens is like, people think we should just change the training objective. But what we see is actually that a lot of these aspects, like, from training data, model architecture, evaluation, all of these change quite significantly when we care about the robust objective as opposed to the standard objective. So I'll try to go over some of these aspects in this talk. So if you look more carefully, at the objective, you see that there's kind of this nice tension where you do have to think about the worst case, because now we're looking at performance not just on one distribution P, but really across all distributions within this ball around the training distribution. But at the same time, we are still anchoring around a particular distribution. So it's not just all inputs, but it's kind of still related to your training distribution in some way. Because if this weren't the case, then there's no way the model would work, because why should it work on something completely different? So you're kind of constraining it to be close to the distribution, but you still want to get something beyond exactly the brittle performance on one distribution. And so, yeah, so a lot of this work is trying to reason about worst case perturbations of somewhat realistic instances. And so kind of modeling this theoretically can be quite interesting and challenging, because we want to balance both these aspects. So in the first part of the talk, I'll focus on the evaluation part and talk about how the worst case makes things challenging in terms of evaluation and understanding if a model is actually robust. And we'll see how we need kind of guarantees on this worst case performance to end what would otherwise be an arms race when we try to make models robust. In the second part, I'll talk more about the statistical part of actually thinking carefully about what are the distributions you're trying to learn and what could be the statistical challenges in trying to learn classifiers that are robust on these particular distributions. So with that, I'll jump into the first part of the talk on adversarial examples, which is a particular notion of robustness. So the setup. So I think the framework is pretty intuitive and easy to understand. So instead of looking at just performance on one particular input to the model, you want to do well on attacks that can perturb these inputs. So as an example, this is a stop sign that a machine learning model would correctly classify as a stop sign. So it turns out you can add small perturbations. For example, you can add these black and white graffiti-like stickers, and the same model would call it a completely different class of speed limit. As another example, you could have a sentence that is correctly classified as toxic, and by just perturbing and adding introducing one typo, you can make it a different prediction. And so abstractly, you have some input, and you define a set of perturbations to this input, and you want to make sure that your model does well on all perturbations. And the way we model this is to say that an adversary can perturb this input to any point within this set, and we want to make sure the model does well. So depending on how we define this set, we can get different kinds of robustness. For example, this could be stickers, this could be typos. And a very commonly studied example is the following, the set of perturbations, which we'll use for the rest of the talk as well. So here's an image of a lakeshore that if you take any good classifier trained on images from the internet today would correctly classify as a lakeshore. But you can change each pixel by a really small amount to get the image at the bottom that still very much looks like the same image and looks like a lakeshore to you and I. But the same model would call it a completely different class of laptop. So precisely the set of perturbations that we'll see is each pixel or each feature can be changed by some small quantity epsilon. which is usually small enough that the images are imperceptibly similar. I think this is kind of an interesting challenge to try to solve because it shows how brittle these systems are, where something that's even imperceptible can really change the model's predictions. And so clearly these models are making predictions in a very different way than we imagined them to. And this is an extremely well-studied problem, and we still don't have a complete solution. And there are like some fundamental challenges like for why this is so hard. And I'll talk about some of these in this talk. But it's pretty like, it's not great that even on this very simple and well-defined situation of robustness, we don't have a good way to achieve this. Okay, so now I'll talk about evaluation and like why we need to think more carefully of how do you even check if a model is actually robust. So here's a brief history on adversarial examples. So like I said, there's been a lot of work in this space. So like what do things look like? In 2013, they were discovered where it was shown that small perturbations can break systems. And the problem was not that we didn't have ideas on how to solve this problem. In fact, very quickly, there were a bunch of different ideas for defenses that were proposed, for example, distillation. But the issue was that it was really hard to say whether whatever was proposed was actually robust or not. So for example, very quickly, it was shown that this idea was actually not robust because you can search for perturbations more carefully and you can break these systems. So the problem was these ideas like defenses were being checked heuristically, like whether they work or not. And if they were not done properly, you could quickly break them. It was not just distillation. There were so many other defenses which had a similar problem. For example, there was a claim in this paper that you don't need to worry if you can see the same image from multiple views or angles and so on, because you have redundant information. And just like 5 days later, this claim was shown to be broken. And in 2018, there was this really nice paper from ICML where 7 different defenses that were published in the previous conference were broken by the next deadline. And so this was kind of really unsatisfying because we had a lot of ideas on how to defend, but the problem was it was really not clear which of them were actually working, and all the defenses that were proposed, they constantly kept getting broken. So the issue here is because we were not reasoning about the worst case properly, and so we try to think about, is there a way we can actually get a guarantee on the worst case performance and put an end to this kind of an arms race between attacks and defenses? So I'll talk about how it turns out that it is actually possible to get a network with guarantees on the worst case performance. And I'll talk about some of the work that we did and the main ideas involved in getting networks with guarantees on their performance. Okay, so the main idea, which probably seems very straightforward to theoreticians, is that yes, we should obviously bound the performance of the worst case attack. And so if we write it mathematically, what we're saying is, since you're allowing perturbations and we're looking at what happens when you make perturbations, we want to make sure that the maximum loss that any adversary could induce within this allowable set of perturbations, that loss has to be small, or let's say that loss has to be 0, if actually the network is robust at that particular point. Because otherwise it's not, because you can always search and find a better perturbation that would break your model. This seems like a very reasonable, straightforward thing to do. And so what we should be measuring is on what fraction of the points are you actually able to make sure that the robust error is basically what fraction of the points there is a perturbation where the loss can be high, because then the attacker could find that perturbation and break your network. But the problem is that computing this loss or computing this maximization over this ball of perturbations is actually an intractable computation problem for particular function classes. And so this was kind of the reason why the straightforward idea that we should just compute this maximum loss is kind of hard to actually do it. And so, the most commonly used models in practice are deep networks. So to get a sense of what that optimization problem looks like, so you have an input that goes through all these different layers and you get an output. And what happens in each of these layers is you have a matrix multiplication and then you apply a nonlinearity. So that's how the input gets transformed to the output. And so now the question is, when you perturb some input, how does the output change? And as you can imagine, because you have these nonlinearities, this whole process of going from the input to the output is now a non-convex problem. And this is a non-convex optimization. For example, the commonly used nonlinearity or activation function is this rectified linear unit, where you are 0 if it's less than 0, and then you are x, or like z if it's greater than 0. So the issue is when you have deep networks, you have these non-convex issues, like you run into a non-convex optimization problem because of these nonlinearities. Yeah.
Why do you care about? If it's hard to find the worst case perturbation, then why do you care if you defend against it? Like your attacker is also in real life polynomially bounded, right? So why shouldn't you care about defending against the worst attack that can be found by a polynomial time attacker?
Right. Yeah, that's a good point. So I guess it depends on how you model the incentives of the attacker. In some points, in some cases, they only care about one particular point that they're trying to break. So you can imagine that they have a lot more resources for one point. So when you're trying to defend, you're kind of trying to defend more globally. So that's one kind of a mismatch that could arise. And I guess the second thing is, from a practical perspective, it's really hard to think about kind of where to draw the line for what's achievable versus not. So I think that's one of the reasons that it's hard to say.
So you have some non-convex optimization problem, but like the conventional wisdom is non-convex optimization is easy, just do gradient descent.
Exactly.
So suppose I did that, and then I get the resulting supposedly robustified network, except I did gradient descent, so I don't really have any certified bounds on how well I did. Can you break those?
Yeah, so that's kind of what was happening in the previous slide, right? So that's exactly the kind of ideas people tried, was like to have heuristic attacks, but like you can just use a better heuristic and break those models. So, but one successful defense that kind of is unbroken in the sense that it doesn't go down to 0, but it still drops if you search more carefully, is to do something like you said, is to do like gradients with descent with a lot of restarts and careful tuning of the step size. And
this is the robust adversarial training, the Madri thing.
Yeah, exactly.
Yeah, okay.
Yeah, but even those things from from my experience, like you can reduce the accuracy by like a few percent points, but just being really careful about your heuristics. So,
okay, but effectively, what would be going on is you're trying to, like, you as the attacker are just trying to do a bit better a job of the optimization problem than was done when in training.
Yeah. Another kind of challenge is that you could still so I guess people usually call this transfer, but you could train your own surrogate model and then try to attack that. And then sometimes it just observe that also works on like a different model as well, because kind of maybe intuitively, like these models are having similar failure modes in terms of what signals they pick up. So that's again something we don't completely understand, and it's hard to say like how. So you could end up having a surrogate optimization problem that's easier, but like somehow things still transfer. So that's another issue.
Thanks.
Yeah, feel free to stop me and ask questions at any point. Yeah, so like I guess we spoke a little bit about this. So exact verification is intractable. And at that time, like some of the combinatorial approaches that, for example, using SMT solvers, like modified for neural networks, only scale to about 100 nodes. And you could use mixed integer linear programming as well, and they also didn't scale very well. So in contrast, the kind of networks that we care about in practice have about hundreds and thousands of nodes. And so there was this huge gap between when you could actually compute the worst case attack and what we were trying to use in practice. So what could we do about this? And so the kind of key idea is that maybe computing the exact worst case perturbation or loss is hard, but you could still get away with actually just computing an upper bound and being conservative. So if you had an upper bound such that if you could say, like, whenever this upper bound evaluated to 0, like the worst case loss is also 0 by definition. And so we know that this function is robust to all attacks. So that was kind of the idea that we pursued. And so, pictorially, so suppose this is kind of what the worst case loss looked like. You could consider some upper bound that looked like this, for example. And whenever this upper bound was 0, you knew that even the true objective is 0. And so you can say that, yes, the network is definitely robust at these points. But you could be missing at some points where actually the worst case loss is 0, but the bound is too loose. And so, going off of that, like we could measure the certified error, which is like what fraction of the points is this upper bound actually greater than 0, because those are only the potentially points that the network could get wrong. Everything else, that the network has to get right. So this is one way in which you can try to avoid this arms race, and like no matter what the adversary does, as long as you have a like a correct upper bound, this would give you something in practice. And so this allows us to give like kind of certificates of performance, which says that if you use this upper bound, you can prove that no attack can get error greater than like whatever certified error you measure. So this is kind of the idea that we pursued on trying to break this arms race. So one way to get upper bounds is convex relaxations, that perhaps a lot of you here are familiar with. And we came up with one upper bound. So I'll present the upper bound later. But like, we had some upper bound where, so like earlier we had this issue that when you have perturbations, the outputs can trace this non-convex set. And so instead of dealing with this thing that's hard to analyze, we have a convex set that surrounds all these perturbations that actually come from the valid set. And you use duality to make sure that you're getting a right upper bound across this entire convex set. That's sort of the idea that we employed to try to get an upper bound and see whether we could prove something about how robust these networks are actually in practice. And so like can go and try what happens with this upper bound. And so the kind of unbroken defense, like in that paper that broke 7 defenses out of 8, one thing that they couldn't break very much was adversarial training, which like Sam was saying, the idea is that you approximate the gradient to the worst case loss and you keep training, and hopefully you've searched carefully enough such that you are caught everything on the training set, and then it kind of generalizes. And so we kind of we computed what are the points where this upper bound is greater than 0, and that gives you the certified error. And when we did that, what we found was that we got something pretty vacuous. So this bound was so loose that it said that every one of those points was potentially attackable. And so we didn't really learn anything, because in practice, it seemed like the network was robust, but we weren't able to really say anything about it using this particular convex relaxation because it was too loose. So this was slightly disappointing. But at that time, we kind of went back and thought, like maybe this bound is vacuous on that particular adversarially trained networks, but could we find new networks where this bound was actually meaningful? So maybe we can't prove something about this network, but can we get new networks where this bound is can be used? And so the idea we pursued was, can we train new networks, or like have a new training process that gave us a network where whatever convex relaxation or upper bound that we used was useful enough to give you something reasonable about the certified error. Right, so the natural idea is that instead of minimizing whatever heuristic that you had before, this minimizes upper bound directly. And so hopefully by minimizing this upper bound, you're forcing yourself to find parameters f where this bound is small. And so that's what we did, and we got this kind of max grad network. So evaluating how well this did in practice, what we found is that now this on this particular network, this bound is actually reasonable. And so we got a guarantee that no attack can get more than 35% error. Whereas in, until then, it felt like when you had a defense, the network could just, any attack could just make it to 0. But now we've got a network with a guarantee using this idea of upper bounds. So this is pretty interesting because, when we think about instances and like finding instances that are easy to solve, this is one way in which that actually played in practice, in that you have an upper bound that's not always tight, but like let's try to find an instance where the upper bound is tight. And because you have control over the training process in many occasions, you can try to find a network where you can prove things about. And so the key takeaway that we found was like vacuous upper bounds actually become non-vacuous when you minimize them while training. And so that led us to this kind of new way of thinking about defenses, in that instead of minimizing heuristics, which is what you typically do, you instead take an upper bound where you can prove things are robust. That bound might not be tight always, but well, you can find a network where that's tight by explicitly minimizing that on your training set. And just to give some concrete numbers. So MNIST is a very common data set in machine learning, where we want to predict which digit, handwritten digit it is. So usually you just measure on this test set. But now we introduce some perturbations. Not sure if you can see it, but there are some small perturbations, and you want to see how well your network does on these perturbations. And so you can compute a certified error using the same idea by using the upper bound, but you get a guarantee on performance. And so using this idea of certified defenses, like this concurrent work from CMU with a slightly larger network, and the same idea. So minimizing this upper bound, you're actually getting somewhat reasonable certified errors, as opposed to the kind of arms race that existed earlier. And since then, there've been a lot of work on using different bounds and scaling things up differently. And pretty much we get like, up to 2% error with guarantees as opposed to what existed before. So just to like place things in perspective, so in 2013, like when these adversarial examples were discovered, there was this kind of an arms race between attacks and defenses. And like, kind of one method that stood out was this work from Alexander Madry's group, where they used a heuristic more carefully and it was not broken, but we had no guarantees on whether it's going to be broken or not. When we tried to use SMT solvers, they didn't scale as well. And so instead of trying to say something about adversarial training, we followed a different route of having certified defenses, where we just trained new networks with the idea that we want to certify them. And so we constructed some upper bounds and then constructed a network where that upper bound is meaningful. And yeah, and so that was kind of, what the landscape looked like at that point. And so since then, there have been a lot of successful applications of this idea to get networks for many different applications. But this question that we had earlier about whether we can say anything about these adversarially trained networks, which is kind of what was most popular and easy to do at that time, we still didn't have an answer there. So this is something that we thought could be interesting to think about, because in practice, we might not always know exactly what method we want to be robust to, or like what is the training process. And ideally, we should be able to say something about any reasonably robust network, for example, that is trained via some heuristic. So going back to that again, the reason previous upper bounds failed was that they were just too loose. And so we can think about, can we get just tighter upper bounds that would work on more networks? So recall that this is the objective, what it looked like. So we had to deal with these nonlinearities or activation functions at each layer. So we try to get a tighter relaxation using semi-definite programming that I'll try to briefly talk about. And since it could be something that's interesting to people here, and this is just one attempt that we made, and would be very interesting to get tighter bounds as well. So if we look at these nonlinear activation functions, for example, the ReLU, this is the most popular activation function used, and this is what it looks like. So the idea is that when we have this max constraint, you can really replace this as the following equivalent quadratic constraints, right? So h greater than 0 and h greater than z kind of make sure that you're always greater than both this line and this line. And the third quadratic constraint makes sure that you're equal to at least one of them. So these quadratic constraints are a way to exactly encode this rectified linear unit constraint here. We haven't simplified anything so far, like this is like the exact same question. But the nice thing about writing it as quadratic constraints is now we can use semi-definite programming as a very natural relaxation of these quadratic constraints. And there's like such a large body of work on SDP relaxations, like, for example, the max cut relaxation. And so the nice thing was that if we can actually think about these activations as quadratic constraints, we can tap into this large body of work on SDPs to try to get relaxations. We kind of tried to do that. And perhaps a lot of you here are thinking about, SDPs don't scale very well as well. Like I'll get to that in a bit. But we just tried to see whether there was any promise in this idea of using SDP relaxations to get guarantees on these kind of nonlinear activations. We took back this adversarial trained network, which didn't have guarantees at that time. We took a moderately sized network. So it's like 4 layers, like 2,000 nodes. It's not the biggest network we use today, but we wanted to see what we can do. And all the previous certifiers, if you recall, were basically vacuous because the bounds were just so loose, but they were mostly based on linear programming, which were way too loose to say something unless you explicitly minimize them. So we tried to see whether there's something we could do with using quadratic constraints instead. And when we used the SDP certifier, we found something pretty interesting, that now we actually got a pretty non-vacuous result. So until then, we didn't know anything about like what's the exact error of adversarial training. But now we could get a bound of 18%, which says that no attack can get error greater than 18%. And it's pretty close to the lower bound coming from attacks as well. Okay, not super close, but it's in the ballpark. So this is pretty promising to us, because if you use only linear constraints, then you could say nothing about networks that were not explicitly trained used to minimize that bound. But somehow using quadratic constraints seems to be useful. We can also prove that for example, random instances on two-layer networks like SDP relaxations, like improve your tightness by square root dimension compared to linear programming relaxations, which is what people were using. And so just to sanity check, we looked at taking different, different other robust networks as well. So it's not just adversarial training. We took at certified networks as well, and we saw something pretty similar, that on a variety of these different networks, this SDP relaxation is pretty tight. And so this led us to pursue, like, can we use this as a way to get meaningful certificates in practice for a variety of networks which might not be trained in any particular fashion. So the caveat is that SDPs seem to be tight, as we verified in small instances, but they don't scale very well. For example, we used off-the-shelf solvers, and like 2000 nodes was kind of the limit at which we could use them. But the nice thing is that there's a lot of structure in deep networks, and I kind of wanted to share that in terms of getting new efficient algorithms, is that we know how to do first-order methods really well with deep networks. For example, a lot of the current implementations, they are highly optimized for taking gradients and training a network. And so like actually running first order methods, for example, for SDP verification, can be reduced to using the same primitives that already are used for training the network. And so that means we can actually run things in parallel, like use optimized implementations, for example, for like convolutional matrices and so on. And so there's actually a lot of structure that could be employed in sort of solving these SDPs for the purpose of verification of neural networks. So we did a very kind of first pass at this. We literally took the simplest first order, reformulation you could think of, and just implemented that using the idea that we only needed forward and backward passes, so which are basically operations we have for training networks. And this also allows us to integrate into modern frameworks. And so in principle, you can run this on any network that you can train. So that's pretty scalable. And this very simple idea allowed us to now scale up to 20,000 nodes and 2 million parameters, which was a huge factor of improvement over what combinatorial solvers could solve. And so this allowed us to actually scale up even more complex data sets like CFAR10 and get guarantees on robustness. So just to complete this picture, we asked this question, can we say something about adversarial training or things that seem like they were useful in practice? And so there was this idea of using quadratic relaxations and getting a tighter SDP certification, which scaled till about 1,000 nodes. But by using first order methods, we're actually able to scale it up further and get something reasonable on networks with up to 20,000 nodes. So I just wanted to kind of reflect on these results and say some open questions where I think especially theoretical insights could be useful, and we don't have answers so far. We go back to this idea of certified training, where we minimize upper bounds on robustness as a way to get certifiably robust networks. One thing that we observe in practice is that doesn't do as well as using heuristics. So somehow running gradient-based search and explicitly minimizing the gradient-based search is much better at practice than actually trying to get an upper bound and being robust to this upper bound. So one issue could be that by minimizing this upper bound, we're kind of regularizing too much, and that we're actually not allowing enough capacity. So that's intuitive, and we don't have a clean way of thinking about this. And so like when we are explicitly minimizing some bound, we're making things easy to certify, but in the process, like what exactly is effective hypothesis class, and is there something we can say about how expressive those classes are? Is that kind of what's the issue?
When you say you don't do as well, that you mean in accuracy, like
in accuracy and robustness, both.
Okay.
Right. So for example, attacks can get, say, these are just numbers at the top of my head, like an attack, let's say, gets 9% on adversarially trained networks. An attack could get like 15% on the certified network. It's just guaranteed to be, say, 15%, but it's still, you can still get that. Yeah. So it's not just that the bound is loose, but the attack performance is also different. So like, I think the networks are actually less robust somehow. And so, yeah. So like, I think, I guess the training error is also like somewhat high for these networks. And so I think there is an issue of expressivity when we use an upper bound. And so the question is like, can we design upper bounds that do not affect expressivity? That would be pretty interesting. And of course, like, another thing that we haven't really thought about is what is the role of the data distribution. So at some point, the network still comes from minimizing some data. So if we make some assumptions on the data, can we like come up with a suitable upper bound such that putting them together, you're not compromising on your performance. And these are things that we don't understand. And I feel like we've kind of hit a ceiling in terms of like how, another interesting property we found was that if you use looser upper bounds, like for example, you don't even do linear programming, you just like propagate box constraints, like just a very simple thing you can do. But that allows you to like train things for longer and train larger networks. And somehow they all come together to get the same performance. So if you use a really complex upper bound, you are restricted in terms of how much you can scale. But if you use a simple upper bound, it's loose, but like you can scale it up. And somehow they all get very similar performance in practice. So there seems to be like some kind of ceiling that we don't really understand where it's coming from. And then like in terms of just general certification, where we don't think about explicit training, the natural question is, how do we get tighter relaxations? How do we get more scalable relaxations? And maybe SDPs are promising, but like, this is just like one attempt. It'd be really interesting to think about better ways to certify these problems. And also, are there some architectures or initializations that can be better? Do we have some guidance on what we can do such that we are able to generally certify things? And the same question from before, we still don't know exactly how do we incorporate statistical structure of the training distribution in terms of like what networks we care about and how do we certify them in practice. Okay, so with this, I'm going to switch gears. So if there's any questions on the previous part, I can take questions. Yeah.
Did you study a little bit some statistics of the networks that you were getting when they were certifiably robust compared to networks that were trained in a more vanilla fashion?
Yeah, so I mean, tried a bunch of things. So like things that come to my mind are, when you try to minimize upper bounds, you find that things are sparse, much like they activate, like there are some nodes that are just always off. But when you actually do the gradient-based search, that is not true. So somehow by using an upper bound, you're kind of inducing much more sparsity than if you weren't using the upper bound. So that was one observation that we found. The other thing is the weights are typically larger, or like the effective margin in the sense that like the output by the norms are smaller when you do adversarial training, even on the original instances. So not just on perturbation, but even on the original instances, you do see that. But that's more related to the generalization part, maybe not as much as like the statistics of the network. But we didn't have any other, like the sparsity was the only thing that we noticed was qualitatively different.
Okay, because I guess intuitively you have this sort of idea that the networks that are trained normally have this weird situation where you have some very quick variation that makes it that you go into another class very quickly. You have these sort of tentacles of and so this is this something that you try to illustrate also a little bit with seeing if this sort of phenomena is something that happens?
I feel like, I mean, it's hard. In some sense, the existence of these perturbations kind of says something similar, like, just the fact that you have perturbations that cross the boundary already intuitively get at that. Yeah, I don't know if, I don't think I have any other like concrete thing to add there.
Okay, thanks.
Okay, cool. So with a better handle on evaluation, like, we can go back and look at how we are actually making things robust. So let's look at a slightly more complex benchmark called CFAR10, which is this image classification data set. So you have 10 classes and you want to predict which of the classes the image is. You can measure the standard error, which is like what % of the test set is misclassified. That's usually what we measure. And we can also look at robust error, which is how well do things perform in the presence of attacks. So you take an image, you allow an adversary to perturb it by some epsilon so that it's still small, and you see whether the network can get it right. If you do standard training, you do pretty well on the test set. So that's why we all think machine learning is great, but things are not robust. So for this part of the talk, just to keep things simple, let's just look at the heuristic performance. So adversarial training, what we see is that the robust error does improve. And this is kind of a rough, like if you do certified error, it will be like worse than this. So you do improve. But interestingly, there's a trade-off. So you see that the standard error increases. So So somehow your robustness has improved, but your accuracy has gone down. And this is not true just for adversarial training. There've been a lot of variations been proposed, and they all show a similar trend where your robustness does improve, but the standard error of these robust models was like 4 times higher than that of the standard models. So this to me was very surprising because I felt like by making things robust, like you should strictly be making the models better because you're trying to force it to not use meaningless perturbation. But somehow we actually saw the opposite in practice. And so this is actually a pretty big problem because no one would want to use robust models if they're going to be less accurate. So I wanted to try to understand like why this even happens and is there something we can do that actually can fix this. And so why is there this trade-off? So at a very high level, what standard training does is you take a training input and then you teach it to get the correct label, like you train a network to get the right label. When you do robust training, you take not just the input, but also a set of perturbations, and you force it to get the right label and all this entire set of perturbations. So why would adding perturbations in this way increase your standard error? So one natural hypothesis is that whatever you're adding is actually wrong. Right? For example, if this is what your data set looked like, so you had this image of a lake, and then you had a perturbation that looks like a laptop. The model correctly called it a laptop initially, but now while doing robustness, you've kind of confused your model. Then, of course, it would make your model less accurate. But this is not what we expect in practice because whatever perturbations we add are actually really small. And if, in fact, like look like this, they're imperceptible. So we're clearly not adding any inaccurate information. So let's assume for now that whatever perturbations we add are accurate. And so by doing this, we are strictly giving more information to the model, we're adding more data. So it's very surprising why models would be less accurate then. So maybe this is because you're adding accurate data, but you don't have enough expressivity. For example, if this is a setting where you only had linear classifiers, if you have to be robust, that means you don't cross any of these boxes, then the only linear classifier that you could have would be inaccurate. It would be something like this, which is inaccurate. If you want to be robust and accurate, you need this nonlinear boundary. And so if you're somehow operating with a model family that's not rich enough, then you could get these trade-offs. But this is also not true in practice because we use really big neural networks, first of all, and so we assume they can express such complex functions. But also on the training set, we observe that we get zero, or like we are able to fit the standard and the perturbations. And so we are not in this kind of a situation. We are able to fit the data. So if you're only adding accurate information, and we also assume that we are well specified and you have enough capacity, then it's very surprising why would adding more information make your model worse, like make it generalize worse. And so in some sense, we thought like this could be because of poor optimization, because there's no other reason this would happen. But when I think about this more carefully, we found that this trade-off can occur even in a convex learning problem, which I found quite surprising because it went completely against my intuition that telling a model to do something reasonable actually made it worse. I want to kind of show the simple construction for where we see this kind of behavior. So the key thing is we work with over-parameterized models, which means that there are many more parameters than training points. So what this means intuitively is that there are many ways to fit the training data. So for example, if this is what your data set was, you could have all these different classifiers, which all fit your training set perfectly fine. And so the question is like when you do some kind of estimation process, which of these classifiers does your model actually pick up? And one way to think about that is to have this inductive bias or norm and say that we pick the estimator that fits the data with minimum norm. So you could have some function that you define that helps to disambiguate which of these ways of fitting the training data actually is your classifier. And so I'll show a simple example where when we use splines, where the inductive bias is to minimize slope changes. So you find the estimator that has fewest slope changes, and that's the way you pick which is your classifier, and how the role of inductive bias can actually play a role in leading to these counterintuitive observations. Here's a simple construction. So suppose this was your ground truth. So you had two classes, and your ground truth estimator had this kind of staircase-like structure. Some perfectly reasonable label preserving transformations are like the ones that are shown here. So these are perturbations which should actually preserve your label according to ground truth. And you try to induce that in robustness, and we can see what happens. So suppose you had very limited training data. So suppose this was all the training data that you had. Let's look at how standard and robust training perform. So if you did standard training, because you're using splines, you're trying to fit the data with minimum slope changes. So you get this blue estimator here, which is the straight line. And you can see that it gets the rest of the line as well correct, and it has low standard error on these like unperturbed points. But it is not robust. Like if you actually draw, like, move things a little bit, like they should have been the same because the ground truth has that structure, but this classifier would get it wrong. And now we can try to fix that by doing robust training, which is, what we do is we add perturbations at training time as a way of telling the model to capture that structure. If you use splines to fit this kind of new training data set where you've added data points, what you'd end up is this green estimator. So that's the way to fit the training data while minimizing slope changes. So you can see that this estimator actually gets the rest of the points wrong. And so here is an example where with the best of intentions, we tried to make the model better by giving it more information. But because of the way the information was used by this splines model, we actually end up making the model worse. Yeah.
Changes, but like I could imagine like this continues as a line that cuts correct, right?
Yeah, so I guess that the splines estimator doesn't do that.
I said the spline will not do it.
Yeah, yeah,
okay.
yeah. Kind of one way that I found useful to think about is like somehow the standard training captures this global structure but misses out on this local structure. And when we tried to improve the local structure or like induce that by adding training data, we ended up compromising on the global structure. And this was because of using splines, which minimize these slope changes. And we can generalize this for noiseless linear regression, where the commonest or like the most standard inductive bias is to minimize the L2 norm. So you fit the data while minimizing the norm of the estimator. And turns out that a quantity that is key in determining whether there is a trade-off or not is the population covariance. Here's an informal theorem where augmentation or adding the data, adding extra data which is accurate, which shouldn't have hurt your model, we can prove that it does not increase the standard error, or it does what you'd expect, only if either sigma is identity, which means the population covariance is identity, or you just have a lot of data and the training data spans all directions of sigma. So if you've basically seen all directions of sigma, you don't have this problem, or if sigma is identity, you don't have this problem. But otherwise, you could be in a situation where adding data increases your error. And so just like parsing this first condition, when sigma is identity, basically this geometry kind of matches the inductive bias, which is also minimizing the L2 norm. So if both of them are basically treating all directions as equal, then there is no mismatch and there is no counterintuitive trade-offs. But if you take this splines example here, the existence of this global structure actually makes the covariance very different from identity, and that's why you could be in danger when you have something like this. Second condition is that the training data spans all directions. So one way to think about this is if we just had a lot of training data where we saw everything that we were to see. For example, if we had the entire line, then adding augmentation shouldn't hurt. And this is kind of our usual intuition. This would be like the classical setting where we're not over parameterized anymore. And so like when you're not over parameterized, any addition of data would reduce your variance and improve your estimation. And so if you had more training data, then that is actually true and you can prove that. But otherwise you could be in a danger of missing or more data hurting your performance. And so with that intuition, we kind of wanted to see, is there a solution that we could come up with that actually enables us to use this intuition to solve things in practice? So if we recall the conditions from the previous slide, we had either limited training data as an issue or this mismatched inductive bias. We don't have a good sense of what is inductive bias of models in practice, so it's hard to try to control that. But this training data is something that's easier to try to fix. So what it says is that if you had more training data, there won't be a trade-off when you try to be robust. And if you try to actually use this idea, that means you should just collect more data, but labels are expensive. So you'd have to go to download images and have crowd workers to label them, which is expensive. So one thing that we explored is like, is there any way we can get rid of this labeling part? And turns out that yes, unlabeled data you can prove is actually sufficient to mitigate this trade-off. And that's much easier to implement because you just have to like source additional data by downloading things from the internet. We don't need extra labels. And the algorithm that achieves this, like mitigates this trade-off using unlabeled data is robust self-training. It's a very simple algorithm that like I'll demonstrate on this particular example from before. So let's collect a lot of unlabeled data. So we have the same labels as before, but now we've collected a lot of unlabeled data. So we have these black diamond points whose labels we don't know, but we know they exist. So it's a two-step process. And in the first step, we just ignore robustness and just train a standard classifier. So just take your labels, minimize whatever loss you want normally, and use that to get a classifier, and then generate pseudo labels on the unlabeled data. So you apply that classifier on whatever extra data that you've collected. So doing that here is you have the straight line that we had before. That's what you would get if you just minimize the use splines on these particular points. Now we use that to get pseudo labels or fake labels on this unlabeled data. So far things have been fine because you've only captured the global structure, but we still haven't dealt with robustness. So let's deal with that in the second step, where now we perform robust training on both the labels and the pseudo labels. So what this means is that you just take any robust loss. Earlier, you would only do it on the labels, but now you've generated effectively pseudo labeled data on the unlabeled extra points that you had, and you do robust training. So doing it here, you would introduce perturbations, not just on the labels, but also on the pseudo labeled points. And now when you fit this splines estimator, you get this red line, or like this, red estimator, which is both robust and accurate. To summarize this, there are two steps. One is just normal standard training on the labels, and then you pseudo label, and then you perform robust training on effectively a much larger data set. So why does this work? Like, why should this kind of bootstrapping make sense? The key idea here is that the standard classifiers, which is what we use in the first step, they're very great at pseudo labeling because the unlabeled data comes from the same distribution as the training data. So standard classifiers are only bad on perturbations. They're pretty good on more unlabeled data from the same distribution. So we can leverage that to effectively get extra labels for free. And maybe robust training is the harder statistical problem, but really we only need unlabeled data because we can generate labels for free. As in this way, we found unlabeled data is especially valuable for robustness. So for example, here, we had no extra labels, just more unlabeled data. We were able to get both robustness and accuracy by using this two-step process. And you can prove this in linear regression that this process would like always eliminate such trade-offs. And the nice thing is this is a very simple idea, so you can actually implement this and see what happens. And we did that, so we collected more images which looked like CFAR10 by sourcing it from the same data set that CFAR10 was obtained from. And this was the table from before, which I will summarize to make it easier. So if you just did vanilla adversarial training with only labels, your standard error went up. And now by using more unlabeled data, you're able to improve both metrics. So you are actually improving on the trade-off because both metrics have improved. So all previous explanations for the trade-off were like, this is inherent and you're always going to drop. But kind of what we found is that it's actually like a statistical problem. If you just had more data, it seems likely that we would be able to improve both metrics. And so in this talk, I only spoke about the standard error. And like you can show a similar idea, like kind of helps for robustness as well. Like, simple mixture of Gaussian setting where there is a provable lower bound on the sample complexity needed for robustness. You can prove that actually only unlabeled data is necessary. So there's no known example of like a gap between robustness and accuracy that unlabeled data cannot solve by this idea of robust self-training. And the current state of the art as well is based on this idea. It's kind of, so this is roughly where things stand now. So we have improved to some extent over adversarial training by using more data. To summarize this part, in general, it's pretty interesting empirical observation that is problematic in that every time we want to improve robustness, the most natural thing you would try to do is to add more data to reflect the structure you want to capture. but that could actually make a model less accurate because of these kind of inductive bias issues with large models. But the nice thing is that with just using extra unlabeled data and this robust self-training, you are able to mitigate some of these issues, which scales up in practice as well. And so to reflect on this part a little bit and stuff that we don't completely understand, one thing that I found interesting is that so far, like this whole analysis studied of noiseless setting. So we assume there's no noise in the data. And if we were in the under parameterized setting where like the number of data points was more than dimensions, if you're in a noiseless setting, you've basically solved the problem. But interestingly, when you're in the over parameterized regime, which is where like a lot of neural networks we think are, even noiseless setting can give you pretty interesting observations, especially because in practice, the labels are typically pretty, like they seem pretty correct. And of course, over parameterization kind of blurs the line between generalization in distribution and extrapolation. Because if you assume there are like some directions or dimensions that you just haven't seen, like do you call that generalization or extrapolation is kind of unclear. So that's something that I feel like, this example went over because we didn't even construct a particular distribution. And in general, and think about robustness, so we care about structure of perturbations relative to the data distribution. And we need to be careful about like what exactly is the structure of perturbations and how does it relate to the original distribution. I guess I don't have time, so I'll skip that part. But in my work, what I found was pretty helpful to deal with this thing is to assume the least possible you can about robustness, which is that it is just anything that's orthogonal to the subspace of your training data kind of falls under the robustness. So it feels like that was one way that we found useful, even for real world distribution shifts, where we had no way of characterizing what the shifts were as a conceptual mathematical model. Thinking of robustness as just orthogonal to your training data was something that was pretty helpful. I guess with that, I will stop because I don't have time, but yeah. And I think in general, like there's just a lot of open problems. Like we don't know how to solve robustness in practice. And some of in my work, I've made really, really simple assumptions or like done very little modeling of what the data distribution or the perturbations are. And I've still found pretty useful insights. And so if we can actually do more careful analysis of like these worst case distributions and perturbations and what role the data distribution plays, I think we could get really useful things that could help us solve these problems in practice. Yeah, with that, I want to thank Google and Open Philanthropy for funding me in this work and my wonderful collaborators.
Great, yeah, thanks Aditi for the very great talk. Any other questions?
You said at some point that all the LP based methods are beat by SDPs. Like okay, I mean, to what extent is there flexibility to design bigger LPs? I mean, somehow LP solvers, there should be some trade-off here. Like LP solvers are probably a lot faster than SDP solvers, so you could imagine designing fancier LPs than the obvious one. Have people tried kind of fancifying the LPs instead of switching to quadratic programs?
Yeah, I think there's one work that I can point you to that characterizes more generally what is the class of LPs for which there is this kind of barrier. So it's not just the vanilla LP, but like you can construct fancier things. But I think you're still limited by the fact that so I think the main issue with, so the main intuition for why LPs fail is that you have all these different nodes in the network, and in linear programs, you can only end up analyzing the nodes kind of independently. Like there's no way to talk about how one activation compares to like how it affects the other activation, because that would make things quadratic. And so in some sense, that's the intuition for why there is this gap. So any linear program kind of cannot reason about things jointly. Or that's very intuitive.
Okay, a related question. When you work in the quadratic formulation, so you actually introduce like pairs of variable, like there's every pair of activations gets a variable?
Yes.
The reason I'm asking this is because there are these works like, okay, there's some paper by Andrea's group, Montanari, where they were thinking about how to implement degree 4 SOS for some image denoising tasks. And the observation was, well, for image denoising, you only sort of like, okay, degree 4 SOS sounds prohibitive, but you only need like to really preserve some local constraints because there's locality.
Right.
And okay, you would think deep nets would have a similar phenomenon that like, this I should care about the joint behavior of this activation and one's near it, but do I care about the joint behavior of this activation and one's far away? Like, do you really need all pairs of variables in your quadratic program?
That's a good question. Yeah, I can't say for sure. Yes, so we haven't looked at that. I think that's a good idea. Yeah.
Okay,
Yeah,
thanks.
Yeah. I think what most matter is if you have like things in the same layer. Yeah, so I think you want to reason about things in the same layer jointly because they all feed into one node. But like maybe like between layers, you might get away with not modeling that. So yeah.
I mean, if they're all feeding into one node, in some sense, they're close, right?
Yeah, exactly.
Like
Yeah, exactly.
10 pops away, like maybe
That you probably don't care. Yeah.
Great. Other questions? If not, let's thank Aditi again.
Thank you.
So we're back at 3:30.